Hi subscribers, welcome to our channel. This is Kishore Palavalsa. Please subscribe our channel for more videos as well as for more information. I need your support always, okay, for the different types of making videos. So please support me always, okay. So now today we are going to discussing about, so there are different types of generated EMF. There are different types of generated EMF equations of different types of generators, okay. Now going to discussing about EMF equation of a generators. Okay. EMF means here generated EMF. EMF means here generated EMF equation. Here we have to generally calculate for the different types of generators. Okay. So coming to the generators. Okay. According to the connection, according to the excitation. Okay. According to the excitation given to the both armature winding as well as field winding. According to the excitation which is giving, excitation means we are given to the external supply, we are given to the external supply to the both armature winding as well as field winding of a generator. So they can be classified into basically two types. They can be classified into basically two types. Okay, one is the self-excited DC generator. Okay, one is the self-excited DC generators, self-excited DC generators. Okay, and second one is the separately excited DC generator. Second one is the separately excited DC generators. Okay, DC generators. So coming to the self-excited DC generator. Okay, coming to the self-excited DC generator. Okay, in that there are different types of generators is there according to the construction of field winding, according to the connection, simply you can call it as, according to the connection of field winding which is in series with the armature or which is in connection with parallel to the armature. There are different types of generators is there in the self-excited DC generator. There are different types of generators according to the construction. There are different types of DC generators is there in that self-excited DC generators. Okay, in that one is the DC series generator. One is the DC series generators. Okay, series generators, which is very important, as well as, and second one is the DC shunt generator, and second one is the DC shunt generators. Okay, and third one is the DC compound generator. Third one is the DC compound generators. Okay, so these are the in the different types of generators. There are individually generated EMF will be producing in that particular armature winding of the rotor, particular armature winding of the rotor of the generator. Okay, individually all those different types of motors, all those different types of generators. Okay, so which is majorly based on the, okay, basically based on the according to the, so connection of field winding, according to the connection of field winding to the armature. Okay, according to the according to the field winding which is connected to the armature. Okay, so that is the different types of generators is there. So coming for the DC series generator. So let us go for the, before going to discussing about all those things, next we are going to discussing about separately excited DC generator. Separately excited DC generator. So in this separately excited DC generator, only one, according to the construction of field winding, according to the construction of separately, according to the construction of separately to the field winding. So the separately excited DC generator is generally acted. Okay, so means here we are also in this also we are separately individual supply we are given to the both field winding as well as armature winding. But in case of self-excited DC generator, here we are totally combining with both armature as well as field winding. Here we are combining to the both armature as well as field winding. So then only we can feeding to the supply to the all those different types of self-excited DC generators, all those different types of self-excited DC generator. But in case of separately excited DC generator, okay, the separately excited DC generator only one machine is there, only one machine is there according to the construction. So in that the field winding which is separately we are given to the excitation as well as the armature windings also we are given to the separately excitation. Okay, so that's why we can call it as separately excited DC generator. Separately excited DC generator. I think you understood what I am saying. Okay, so let us going for the discussing about the DC series generator. Okay, so in that self-excited DC generators. Okay, so coming for the DC series generator. Okay, coming for the DC series generator. Okay, in DC generator, so simple you can call it as, okay, DC series generator. Here the armature winding which is in series with the field winding. Okay, here so DC series generator means here the field winding, simply here the field winding which is connected in series with the armature. The field winding which is connected in series with the armature. Already know that. Okay, I think. So this is the rotor. This is the rotor, like a DC generator rotor. That is like a DC generator rotor. Okay. So on that rotor, which winding generally winding on the rotor generally winding on a armature winding in case of DC machines. Already in the previous sections already we are discussing different types of classes. Okay, if you want to learning about the depth of the DC machines, I mean DC generators, please go through our previous videos classes. Okay, now you can clarify, clearly. Okay, so now if you want to go for the DC generator, so this is like a rotor of the DC generator. Okay, this rotor which is may contains armature winding. Okay, so like this, the rotor which is may contains like a armature winding. So here, so the armature winding which is winding from first instant, from this instant to like this, we have to winding the entire rotor like this. For example, let us consider. Okay, so here the two ends will be coming here. The two ends terminals will be coming to the on the rotor, entire rotor on the rotor. So this is the one end and this is the one end terminal of the particular armature winding. So this terminal can be I have tension. This terminal can be I have tension, or else stretched, or else like a stretched. సాగదీశాను అంటున్నాండి. ఓకేనా, సాగదీశాను. అప్పుడు ఏమవుతుంది? సో one winding which is go for like this straight. If I kept one winding which is straight and another winding terminal which is will be lagging to the downward side. Okay, so like this. So one winding will be coming like that and the other winding coming like that. Okay, so this is the simply representation of armature winding. This is the simply representation for the calculation of generated EMF in that particular series generator. Okay, all machines also may contain. This is the representation is the same. This representation is same. Okay, so coming to the here, so okay, this is the armature. So simply you can represent it to this motor. Okay, simply represent it to this generator. Okay, like this. Okay, so this is the generator. Okay, so this generator may contains armature. Okay, so I already know that. So one terminal is coming from the top of the rotor and second one terminal is the coming to the downward of the generator rotor. Okay, here we can simply indicate as like this. We have to simply indicate as like this. Okay, so this is A and this is AA. This is A and this is AA. Why? Because the armature windings or the armature terminals which is indicated as one terminal and which is indicated as A and another terminal which is indicated as AA. Okay, please remember that, very important. This is the indication of armature winding terminals of both ends. This is the indication of armature terminals of both ends. One is the A and second winding end is the AA. Okay, let us consider. So here A and AA. As well as, so this is the armature will be there on the rotor. Okay, so and another winding is there. Already know that in any machines basically two windings is there. One is the armature winding and second one is the field winding. Both AC machines as well as DC machines. Okay, so coming to the here, so the armature winding here, the armature winding which is connected to the in series with the field winding, or else we can simply say that in different view. Okay, here the field winding which is connected in series with the armature. Here the field winding which is connected in series with the armature, then only called as it is as DC series generator. Then only it is called as DC series generator. Please understand what I am saying. Okay, please remember that all those points. Okay, here the field winding which is connected in series with the armature, then only we can call it as DC series generator. According to the connection of field winding, there are different types of generators is there, like series generator and shunt generator and compound generators is there. Okay, this is a DC series generator. Okay, so this DC generator already know that from the rotor of the generator, some supply will be existing basically in that rotor. Supply means here some generated EMF. Supply means here some generated EMF will be existing in that particular rotor. So due to that resultant, some voltage will be existing. Due to that voltage, resultant some current will be existing. That current will be goes to the load centers. How do you know that? That current can be finally goes to the load center according to the construction of generators. According to the construction of generators. So all those things we are learning the in previous session classes. Okay, please go through it if you have any doubt. Okay. So here also, so the armature windings. So from that armature winding, the some voltage RS like a current will be existing. That current will be finally goes to the we are fetting to the load center. Okay, that is the purpose of generator basically. So finally, which is goes to the load center. Finally, the total supply RS like a voltage or current, which is going to the like a load supply, like a load supply. Okay, like a load supply. Here, load is this load is simply we can indicate as like a V. Means load means here some supply voltage or else like a current which is going from the particular rotor of the armature. That's why simply we can get as this is the voltage or load voltage or load current. So that's why we can indicate as like V. So this is like a voltage. If suppose this is like a voltage, simply we can indicate as like plus and minus. Simply we can indicate as like plus and minus. Okay. As well as here, okay, this is the total representation of series generator. As well as coming to the rotor of the armature, coming to the rotor of the generator. In the rotor, okay, basically produced as a generated EMF. In that rotor, basically produced as a generated EMF. Why? Because in that rotor may contains armature winding. In that armature winding, generally some flux will be existing. Whenever we are supply given to the stator winding of the generator, then only some flux will be existing in the stator. Thus, that flux will be cut to the rotor winding of the armature. That flux will be cut to the rotor winding of the armature through the media of air. Already know that, I think. Okay. So that's why in that rotor of the armature, some flux will be existing. Due to that flux, resultant some EMF will be existing. Okay. Due to that EMF resultant, some voltage will be existing. Due to that voltage resultant, some current will be existing. Already know that these are the all different types of transformations of conversion. Simply conversions. All those different types of conversions will be takes place on the particular rotor of the armature. Okay. I think you understood what I am saying. So in this flux, in the some EMF will be existing. In that rotor of the armature, some EMF will be, means that EMF is called as generated EMF is produced. That is given as EG. EG means generated EMF. EG means like a G means generated, E means EMF. Okay. G means generated, E means EMF will be existing. Okay. So this is the generated EMF. So this generated EMF also called as like a voltage. Why? Because due to that EMF resultant generally either produces as either voltage or current. That's why. So this EMF also called as like a resultant voltage. So that can be indicated as like plus and minus. That can be we have to indicate as like plus and minus. Okay. Please remember that very important all those points. Okay. That is indicated as plus and minus. Okay. Why? Because this is like acts as a battery. The EMF here in that particular armature winding on the rotor. As well as coming to the terminal indication of field winding. So here from the armature, some current will be flowing to the field winding. From the armature, some current will be flowing to the in series with the field winding like this. Okay. So in this flowing current basically I. For example, let us consider some I. Why? Because the current which is indicated as I indication. Okay. That's why some current will be flowing to the field winding from the armature. Okay, this is the series field. This is called as series field winding because which is connected to the in series with the armature. That's why which is called as series field. Okay, series field winding. So that's why here. So this is the series field winding. So that's why SERIES field, series field winding. So that's why we have to take the starting two words like a SC. So that's why we are taking to the starting two words, okay, that is like SC. Okay, here taking the SC. So this is the series field winding. So from the series field winding, so throughout the series field winding, some current will be flowing. That is indicated as I. So then the total current which is flowing to the entire series field winding, which is given as ISC. Okay, I think you are understand what I am saying. So the total current which is flowing to the series fielding, which is given as ISC. Okay, as well as. So finally, which is goes to the load center. load center. Okay, and also another thing is there, this is like a armature. So in that rotor also may contain armature. Okay, so that is indicated as IA, why? Because in that the armature winding is there, the armature, in that armature winding some current will be initially existing, the current will be, so finally simply finally some current will be existing, that current will be goes to the load center, already know that. So that current will be given as armature current IA, that current will be given as IA. Okay, as well as the armature may contains internally some resistance also, the armature winding internally some resistance property also, that is given as RA, RA. Why? Because so A means here armature, so the armature may contains internally some resistance property, so that's why we are generally given as R, that is indicated as R. Okay, that is given as R into A, okay. So in that armature some current will be producing, that is given as IA, and also some resistance may contains, that is given as RA, IA into RA. Total armature the armature total voltage drop, the voltage drop which is existing, that particular armature will be given as IA into RA, according to Ohm's law, V is equal to IR, already know that. So that's why the total voltage drop which is existing in that particular armature which is given as IA into RA, okay. So this is the all of the representation. As well as coming to the field winding, here supply will be flowing from the armature, okay, from armature to like this. So that's why we have to indicate as plus and minus, that's why we can indicate as plus and minus. So because here the current will be entering to the field winding, so here entering means here we have to indicate as plus. Here the current will be leaving from the winding, that is indicated as a negative sign, okay. Please remember this. As well as this is like a battery plus and minus, as well as here armature is there, in the rotor, so that is indicated as, so here current is entering plus and leaving negative. Current means either voltage, okay, here entering plus and leaving negative, here entering plus and leaving negative, as well as. So coming to the EMF equation of a generator, let us know we have to calculate it here. So applying KVL to the entire loop, okay. Sorry, know that. So please remember that all the indication which is very very important for the calculation of a generated EMF for the DC series generator, okay. So let us consider, already know that this is IRA, already we are representing, this is field winding. So in this current ISC into and internal resistance is there, that is like a RSC, okay. So now we are applying KVL to the entire loop equation, okay. Entire loop means here like a closed loop circuit, the loop means here itself one closed loop circuit, okay. So let us apply KVL means Kirchhoff voltage law, Kirchhoff voltage law, okay. So all those about different types of Kirchhoff current law as well as Kirchhoff voltage law already we are learning in the previous sessions, okay. Please go through once and you have to learn the, so how to calculate the Kirchhoff voltage law as well as how to calculate the Kirchhoff current law. Please once to go through our previous videos, okay, previous video classes, okay. Now apply KVL, okay. So this is all those we have to indicate as here, okay. Let us know. So from this instant, okay, so generally here we have to calculate the, so the total voltage, Kirchhoff voltage law means voltage we have to calculate it from the positive sign. So generally we have to calculate from the positive sign, or else we have to calculate from the negative side of the voltage, okay. Either we have to starting from this positive sign to remaining all those things, as well as or else we have to start into the negative supply or negative terminal to the remaining all those equations, all those different notations of the total entire generator, okay. So let us know for the calculation shortcut method, we are generally following to the negative terminal of a DC generator, negative terminal of a load, like a load of the DC generator. Let us wait to starting from this, here we have to equation, okay. So from this equation simply we can say that, okay, okay, from this equation first we are giving according to Kirchhoff law minus V. Why? Because this is the minus terminal here, so the load voltage is V, that is given as minus V, okay. This is minus terminal, the supply load voltage is V, that is given as minus V, okay. As well as coming to the current which is flowing like this, okay, from this like this. So the current which is flowing, so through armature winding to field winding to load positive and entering positive to load leaving terminal negative to like this. So let us, we are starting from this instant, జనరల్గా మనం ఇక్కడ నుంచి స్టార్ట్ చేస్తామండి కరెంట్ ఈక్వేషన్ అనేది. ఎక్కడ నుంచి స్టార్ట్ చేసుకోవచ్చు, ఎక్కడ నుంచి స్టార్ట్ చేయొచ్చు, ఎక్కడ నుంచి స్టార్ట్ చేయొచ్చు. బేసిక్గా మనం నెగిటివ్ టెర్మినల్, లీవింగ్ టెర్మినల్ నుంచి మనం సో జనరల్గా వోల్టేజ్ లా అనేది మనం స్టార్ట్ చేస్తున్నాం, వోల్టేజ్ ఈక్వేషన్ అనేది. ఓకే, అందుకే మైనస్ వే అయింది. ఓకే, యాజ్ వెల్ యాజ్ కమింగ్ టు ద జనరేటెడ్ ఈఎంఎఫ్, కమింగ్ టు ద generated EMF. Okay, this is the first terminal, this is taking second terminal. Here taken to the second terminal, that is given as minus V. As well as here also we have to take into the second terminal. Here also we have to take into the second terminal. Please remember that, very very important. So this is the first terminal as well as this is the second terminal. Why? Because the current which is flowing like this, the current which is flowing to the like this entire loop. That's why this is the first terminal, this is the second terminal. This is the first and this is the second. So that's why which is given as plus Eg. That's why which is given as plus Eg. Okay. As well as coming to the here armature. Coming to the armature. Okay. So armature is there. That is it as simply we can indicate as this is plus and this is minus. Already know that. For the armature terminal indication, this is plus and as well as this is minus. For the battery indication, this is the plus and this is the minus. Why we are putting the plus here? The current which is entering to the throughout the entire loop to armature like this. Okay, that's why. So entering of the armature which is given as positive and as well as the leaving of the armature which is given as negative. Okay, that's why we are putting the equation here generally. So plus Ia into Ra, plus Ia into Ra. Why? Because the armature may contain some resistance as well as some current also. That's why Ia into Ra. Okay, as well as coming to the here series field winding. Coming to the series field winding here. So here we have to take into the second terminal. All those different conditions we have to take into the second terminal. Okay. So here current is there, that is given as minus I to Ia into Ra, minus Ia into Ra. Why? Because so this is the plus, this is the minus. Why? Because here we are taking to the second terminal. Here we are taking to the second terminal. Okay, that's why this is the first terminal and as well this is the second terminal. So that's why here indicated as a minus I into Ra, minus Ia into Ra. Remember this, very very important. As well as coming to the field winding, this first indication as plus. Why? Because the current which is entering here to field winding plus and minus, this is given as. Here taking to the also second terminal. This is the second terminal and also this is the first and this is taking the second terminal as well as this is the first terminal as well as this is the second terminal. So that is given as minus Isc into Rs. That is given as minus Isc into Rs. Why? Because second terminal we are taking here minus Isc into Rs. Okay. So this is the equation for the DC generator. This is the equation for the DC generator. Okay. So here we have to calculate to the generated EMF. What is our ambition? Main ambition. Here we have to calculate to the generated EMF, that is given as Eg. That is given as Eg. So from this equation we have to calculate the generated EMF for the DC series generator. Eg is equal to, okay, what happened here? Eg is equal to, so total equation we have to shift that from the outside. So then only we can get to the Eg is equal to V plus minus Ia into Ra means plus Ia into, okay, Ra plus Isc into Rs. Okay, here Eg is equal to V plus Ia into Ra plus Isc into Rsc. So this is the generated EMF equation for the DC series generator. This is the generated equation for the generated EMF equation for the DC series generator. Okay, very very important equation for the DC series generator. As well as coming to the here, one consideration is there. One consideration is there. So here the armature winding. In that armature winding, generally produced current. In that armature winding, generally produced current that is given as Ia. Okay. As well as in this field winding, generally produced current is Isc. Generally produced current is Isc. So here Ia is equal to Isc. Here Ia is equal to Isc. Okay. Why? Because both are which is current in series. Both are which is current in series. Both armature winding as well as field winding. Those are which is current in series. That's why in series the total which is total current will be total flowing to the entire all windings, which is equal, both armature winding as well as field winding which is equal current in case of series winding. In shunt the current will be different. Okay, in shunt field winding the current will be different. In series, coming to the series, here the total current will be same. So that's why Ia is equal to Isc. Ia is equal to Isc. Okay, so from this equation you have to dump this. From this equation you have to dump this Ia is equal to Isc. Then we can get to the total final generated EMF equation for the DC series generator. DC series generator. Okay, so let us Eg is equal to, so V plus, okay, here Ia is equal to Isc. Here Ia is equal to Isc. Okay, so that's why plus Ia into Ra plus Ia is equal to Isc. Here Ia is equal to Isc. So instead of Isc, if we want to place the Ia, instead of Isc, if we want to place the Ia, then we can get to the Ia into Rsc. Then we can get to the Ia into Rsa. Very very important all those equations. So therefore from this equation Eg is equal to V plus, okay, so if you want to take the common to the Ia here, Ia armature current, okay, then we can get to the Ra plus Rsa, Ra plus Rsa, Ra plus Rsa. Okay, this is the general EMF equation for the DC series generator. Very very important. This is the very very important. As well as here some brush contact drop also adding. Here also some brush contact drop. Why? Because the total rotor which is connected to the brushes. So this is called as brushes. So armature winding means, so on the top of the armature winding, from that armature winding, after that the brushes is collecting. Why? Because the total current, how much amount of total current will be existing in that particular rotor of the armature, that can be collected by the brushes. That can be collected by the brushes. So that can be, so that's why simply you can call it as like a, this also B1 and B2 brushes. This is like a, simply you can also call it as like a B1 and B2 brushes. So that's why we have to add to the brush contact drop also. From this equation we have to add to the brush contact drop also. So that is like a, either like a BCD, like a BCD, or else like a B1 and B2. B1 and B2 are RS plus BCD అని మనం ఇక్కడ యాడ్ చేయొచ్చండి. ఓకే, ఎందుకంటే మనం బ్రష్ కాంటాక్ట్ డ్రాప్ ఇక్కడ మనం యాడ్ చేయాలి. జనరల్ ఈఎంఎఫ్ అని మనం ఫైండ్ అవుట్ చేసినాడు. జనరల్ ఈఎంఎఫ్ అని మనం ఫైండ్ అవుట్ చేసినాడు. ఓకే, సో let's now we are going to discussing about DC shunt generator. DC shunt generator. Okay, so coming to the shunt generator here. Okay, same all indications of both voltage and current, armature current indications, all load voltage indications, all are same for the both series and shunt and compound generators also. Okay, so let us going for the DC shunt generator here. Okay, DC shunt generator. In this, okay, in this, so here first of all we have to draw the rotor also. First of all here we have to draw the rotor also. So already know that this is the brushes are also called as like a armatures. Okay, so that is given as Ia into Ra, Ia into Ra. Already in the previous series generator already we are discussing the all those different types of indications, all those different types of indications. Okay, and also this is the general EMF, that is given as plus and minus, that is given as plus and minus. Okay, here so if it is like a DC shunt generator, the field winding which is connected across over shunt or else called as parallel to the both ends of the armature terminals, both ends of the armature terminals. Okay, so here the field winding which is connected across the both armature terminals, across a shunt or else also called as parallel to the both armature terminals. This is one on the armature terminal, this is one armature terminal. Okay, here the field winding which is connected across the both armature terminals like this, across the both armature terminals like this. This is called as shunt generator. This is called as shunt generator. Okay, according to the connection of field winding, the field winding which is connected across the both armature windings of the generator is called as DC shunt generator. As well as here also load is there. Here also load is there. Why? Because so from the generator EMF will be producing in that particular generator. Okay, so generator here also the total current which is flowing to the load, which is total current flowing to the load. So that's why here load also there. That's why here load also there like this. Okay, that's like this. Okay, here this is load. So this is indicated as plus and minus. Already know that. Okay, so this is V and this is the load voltage V, plus and minus. This is the IRA. This is the shunt field winding. This is the shunt field winding. Okay, that's why which is given as IHS. This is which is given as ISH. Why? Because that's the total current from the armature will be flowing like this. So from this particular here some junction is there. From this junction the current will be dividing like this. The current will be dividing. Some of the current will flow into the, some of the current which is flowing to the shunt field winding, as well as some of the armature current which is flowing to the load. Some of the armature current which is flowing to the load. Okay, here the current will be dividing, means here acts as like a junction point. Okay, so whenever the current will be flowing to the particular shunt field winding, shunt field means SHUNT, shunt field winding, FILD field, shunt field winding. So that's why we are taking to the two words of the total. Two words means two particular words of the particular overall entire sentence. So that is given as shunt SH. So the current flowing through the this field is given as I. So then we have to simply we can give the equation like ISH, I into SH. Shunt field means SH. So that is given as ISH. That is given as ISH. As well as this field winding may contain some internally some resistance property that is given as R into SH, RSH. So resistance means internal resistance means that is given as R, as well as shunt field means that is like a SH, that is given as RSH. So ISH into RSH into RSH. This is the total voltage drop across the armature terminals. Total voltage drop which is given to the across the armature terminals, which is given as ISH into RSH. Okay, V is equal to ISH into RSH. According to Ohm's law, V is equal to IR. That's why ISH into RSH. V is equal to, okay. As well as here IA into RA. Okay, so this is the representation. As well as applying KVL to the loop equation. Applying KVL to the entire loop equation of a DC shunt generator. Why? Because here we have to calculate to the generated EMF. Here we have to calculate to the generated EMF. Okay, so that's why we have to calculate here. That's why applying to the loop equation. Here one consideration main is there. Here the loop equation is only which is applied to the load side only. Only load side the loop equation is only applied. Not we are applying to the so field winding side. That doesn't which is applying to the field winding side. Okay, does not we are applying to the field winding side. Okay, only we have to apply to the KVL equation only load side only. Okay, so applying KVL here. So we can simply say that the equation of easy generating EMF. So this is from this equation generally given as first of all V minus V. Okay, from this instant we have to start in the so total entire equation. So this is given as minus V. Okay, so plus Eg. Okay, so this is the battery. So battery indication is doesn't change. Okay, plus Eg. Okay, as well as here armature is there. So that is given as plus and minus. So because current will be entering like this from this direction. Same from previous like series generator. Okay, so that's why here given as like a so this is entering plus and minus. Here taken to the second terminal. That's why taken as a minus IA into RA. Anything is there here? No, anything is not there here. Only minus V plus Eg minus IRA, that is equal to 0. Okay, so this is the KVL equation from the DC shunt generator. This is the KVL equation for the DC shunt generator. I think you are understood what I am saying. Okay, very important which is okay. So from this equation we have to calculate to the generated EMF. So that is given as Eg. Eg is equal to what happened here? V plus IA into RA. Eg is equal to V plus IA into RA. This is the generated EMF equation for the DC shunt generator. Okay, as well as here also some brush conduct drop is there, that is given as some BCD or like some B1 plus B2 or some B1 B2, simply you can call it as B1 B2 or also called as like a BC drop also we are adding here. Why? Because with the help of brushes we can collect the total current from that particular rotor of the armature. That's why we are here adding to the BCD also. Okay, so this is the equation of DC shunt generator. Okay, and also coming to, if we want to for example calculate to the voltage, if we want to calculate to the for example current, how much current will be flowing to the entire field winding for example. So that is given as according to Ohm's law. That is given as according to Ohm's law here. Okay, according to Ohm's law here. Okay, according to Ohm's law, what happened here? V is equal to IR. According to Ohm's law, V is equal to IR. So that is equal to I is equal to V by R. That is from this equation I is equal to V by R. So from this instant also, so here I is equal to I means here ISH. I means here ISH is equal to, okay, ISH is equal to what happened here? Total, what is the total voltage? Load voltage, that is given as V. ISH is equal to total load voltage V by. So what is the total shunt field resistance? That is given as RSH. Okay, this is the total shunt field current. We have to calculate it like this way. ISH is equal to V by RSH. Okay, so this is the equation. As well as so from this coming to the junction here. So for example from the armature, from the current will be from the armature flowing is IA. From the armature the current will be flowing to the IA like this. IA is equal to what happened here? IA is equal to, so this is the load current. Why? Because the total current will be, some of the current will be flowing to the load as well as some of the current which is flowing to the entire field winding. So this is IL as well as this is ISH. This is ISH as well as this is IL. Load voltage is V, voltage is VL. Load current is IL. Okay. So from this equation, how can we write them? IA is equal to, from this junction, IA is equal to IL plus ISH. IA is equal to IL. Why? Because the total current which is here dividing, some of the current to the load as well as some of the current to the field winding, shunt field winding. So that's why IA is equal to IL plus ISH. IL is equal to IL plus ISH. This is the current equation from the particular armature winding of the rotor, as well as this is the shunt field current. If you want to calculate the shunt field current, that is formula IS is equal to V by RSH. Okay, so this is the overall generated EMF equation formula, as well as shunt current formula, shunt field current formula, as well as armature current formula for the DC shunt generator. Okay, I think you are understood what I am saying. Okay, if you have any doubt, please put on the comment. I will give the reply. Okay, if any problem, if any have doubt in that particular solutions, you can simply put on the comment. I will give the reply, no problem. Okay, I can solve all those things. Okay, so as well as next we are going to discussing about DC compound generator. Next we are going to discussing about DC compound generator. Okay, so this is the last one in the self-excited DC generator. In the self-excited DC generator, this is the last one. Okay, next one is the DC compound generator. Compound generator. So coming to the DC compound generator, compound generator here, which is entirely different from the both series generator as well as shunt generator. Both series generator as well as shunt generator, which is entirely different. Why? Because in this compound generator, basically we are using two field windings. Okay, in this compound generator, basically we are using two field windings. Okay, two field windings as well as one armature winding. Okay, previous that in the series and shunt only we are using one field winding as well as one armature winding. But coming to the compound generator, in this we are using two field windings as well as one armature winding. So coming to the construction point of view, okay. So basically, so in the compound generator, basically according to the connection of field winding, in the compound generator, basically there are two types. Okay, so that is, one is the long shunt compound generator. One is the long shunt. Okay, one is the long shunt compound generator, and second one is the short shunt. Second one is the SHRT short. Second one is the short shunt compound generator. Okay, one is the long shunt and second one is the short shunt compound generator in that compound generator, according to the connection of both different types of field windings as well as armature winding. Okay, so coming to the long shunt compound generator, here we have to draw the overall diagram. Okay, so this is like a rotor, already know that. Okay, this is the generator rotor. Okay, in that rotor may contains some armature terminals A, as well as some brushes also there. Okay, as well as here also coming to the long shunt compound generator here. Okay, long shunt compound generator. Here one field winding which is connected in series with the armature. One field winding which is connected in series with the armature. Okay, one field winding which is connected in series with the armature, as well as another field winding which is connected. So one end of the series field, as well as another end of the armature terminal. So if you want to connect like this is called as long shunt compound generator. Okay, which is very, very important. Okay, please remember this. As well as, so here load also there. That is we have to indicate as like this. Okay, so this is the total representation for the DC long shunt compound generator. Okay, here also we have to apply to the KVL to the load side only. Here also we have to apply to the in any machine. Basically, if you want to calculate the generated EMF individually to the all different types of machines, so machine should be, we have to calculate to the load side. Why we have to calculate the load side here? So because the total supply which is going to the load, so that's why we have to calculate to the load side only. Okay, okay, so it was the so now we have to calculate the total EMF equation, easy. So here, so these indications plus or minus in previous sections, how to we have to indicate the all those terminals. Like this also we have to indicate to the all those terminals. Okay, this is plus and minus, this is given as V. Okay, as well this is the IA into RA. Why? Because this is the armature may contains current as well as some resistance property, and also this is may contains EG. In that armature maybe some flux will be existing. That flux will be finally we have to simply called as generated EMF. That is given as EG, which is given as plus and minus. As well as here series field is there. In series with the armature, some series field also there. That is given as a ISC into RSC. That is given as ISC into RSC. Like a DC series generator. Like a DC series generator. ISC into RSC. Okay. Because in this current will be flowing some I. This is the series field. That is given as I into SC. ISC. As well as some resistance internally. Some resistance property is there for this winding. That is given as R. As well as this is the series field. That's why it's given as RSC. So the total will be given as ISC into RSC. According to Ohm's law. V is equal to IR. Please remember that formula. Very, very important. Okay. ISC into RSC. So from this instant, so as well as, so coming to the field winding, coming to the shunt field winding, which is given as ISH, which is given as ISH as well as, okay. So this is ISH, simply as well as some resistance property is given as ISH into RSH, ISH into RSH. Similarly, like a shunt motor, like a shunt generator, okay. So applying the loop equation here, applying the KVL equation here, what happened here? What happened here? Okay, so minus V from this equation, minus V, first of all we have to draw the minus V, as well as here also we have to come into the, so plus EG, okay, EMF equation plus EG, okay, minus IA into RA, minus IA into RA, okay, as well as, so minus ISC into RSC, minus ISC into RSC. This is the equation for the long shunt compound generator. This is the equation for the long shunt compound generator, okay. Okay, so from this instant total equation we can get to the generated EMF, that is given as EG. EG is equal to what happened here? V plus IA into RA plus ISC into RSC. ISC into RSC. This is the total equation for the EMF equation for the long shunt component generator. Okay, so this is similar to the like a DC series generator equation. This is similar to the like a DC series generator equation. Okay. Here also you can know that here IA is equal to ISC, IA is equal to ISC, already know that. So from this equation, EG is equal to V plus IA into RA plus ISC is equal to, instead of ISC, we have to place to the IA. So IA is equal to IA into RSC. Okay. So therefore EG is equal to, what happened here? V plus IA into RA plus RSC. This is the total EMF equation for the DC compound generator. DC compound generator, long shunt compound generator, okay, long shunt compound generator. As well as coming to the shunt field current, if you want to calculate to the shunt field current ISH, okay, ISH is equal to here total load voltage, supply load voltage V by RSH, V by RSH, okay. This is the shunt field current calculation, okay. This is the shunt field calculation, as well as this is the total generated EMF, for the long shunt compound generator, So let's now we are going to discussing about short shunt compound generator, okay. So if you after this diagram, so in this small, if you want to do the small modification, then only we can get to the short shunt compound generator, So let's now, so this signal, the field terminal, if you want to connect it to the both armature terminals, if you want to connect to the both across the armature terminals, the field winding here like this, so then only it is called as short shunt compound generator, okay. Here also the load also which is connected in series with the field winding, and also the another field winding which is connected across the both two armature terminals, So this representation is called as short shunt compound generator, okay. So if you want to go in for the EMF equation, okay, so let us like this here. So applying KVL, the loop, already know that we have to apply any situation generally to the KVL equation to the at load side, So from this instant, so what happened here? So minus V, the EMF equation which is given as here minus V, okay, as well as plus EG minus IARA, okay, minus IA into RA. Then what happened further? Next one, minus ISC into RS, This is the equation for the EMF equation for the generated EMF equation for the short shunt compound generator, So from this equation, EG is given as EG is equal to what happened here? V plus IA into RA plus ISC into RS, Okay, this is the generated EMF equation for the short shunt compound generator, Okay, but here not equal to the IA is equal to ISC. Here not equal to the means here IA means armature current is not equal to the series field current. Why? Because here the armature current here splitting into the sum of the current which is going to the shunt field as well as sum of the current which is going to the series field. So that's why here the IA is not equal to ISC. Here IA is not equal to ISC. IA is not equal to ISC in case of short shunt component generator. In case of short shunt component generator, this is very important. Please keep this point very important. Okay. If suppose in the long shunt component generator, in that IA is equal to ISC. If it is like a short shunt component generator, in this IA is not equal to ISC. Why? Because here the current total will be splitting parallelly. It is splitting, which is splitting like that. Okay. As well as, so coming to the, for example, if I want to calculate the current here, if we want to calculate the current means shunt field current here. In case of short shunt component generator, then what happened here? ISC is equal to V plus ISC into RSC. ISC is equal to V plus ISC into RSC by RSH. Okay. So this is the current equation for the short shunt component generator. Current equation for the short shunt component generator. So how we can get like this equation? Here the total series field winding which is in series with the load here. If you observe this diagram, you can clearly understand. Here the series field winding which is connected in series with the load. So that's why V plus ISC into RSC. V plus ISC into RSC. Will be coming like this by RSH. According to Ohm's law, IS is equal to V by RSH. IV is equal to V by R. Already know that. So IS is equal to V plus ISC into RSC by RSH. This is the current equation for the short shunt component generator. This is the current equation for the short shunt component generator. Okay, Emf equation is and short shunt as well as current equation like this. Okay. So this is the today our class friends, all Emf equations as well as, so coming to the another one is there like a separately excited DC generator, like a separately excited DC generator. The separately excited DC generator which is not used in any industrial purpose or like a domestic purpose or any, so different types of load areas which is not used. And also we can't calculate to the Emf equation in case of separately excited DC generator. In case of separately excited DC generator. Okay, only we have to calculate the, so different types of generated EMF equations only in the self-excited DC generators only. Self-excited DC generator equation like series and shunt and compound. Only we have to calculate the EMF equation. We doesn't calculate to the EMF equation in case of separately excited. Why? Because in that separately excited, both field winding as well as armature winding which is separately isolated. That's why we can't calculate it, and also which is not applied to the any different types of industrial loads or commercial loads. That's why we can't measure to the EMF equation in case of separately excited DC generator. Okay. So this is today our class friends. Okay. So I think you are understood what I am saying. Okay. If you have any doubt, please put on the comment on the comment box. Please put on the comment on the comment box. I will give the reply. I can give the solution for every question to you. Okay. And also please subscribe our channel for more videos as well as for more information, and also for new concept oriented I can put in front of you the different types of new concept oriented classes. Okay, so please support me as well as encourage to me. With your encouragement I can put the different types of new concepts. Okay, so thank you subscribers as well as thank you friends, as well as if suppose anyone not subscribed till now, please subscribe. Okay, please support me. Thank you one and all. Thank you.